here we will try to answer the question that we just end up with. Just a quick refresher. What are we trying to do? So we have these two graphs, let's say G and H. By visual inspection, you can see that they are isomorphic, right? I just draw them a little bit differently. And in this case, because they are isomorphic, I should get the same representations, right? So if I compute vector representations, graph level vector representations, they should be identical. This is good. Yeah, isomorphic graphs, I get same representations. In the other direction, we argued that if I have these two triangle graph and the hexagon, the graph neural network cannot distinguish them. It maps them to the same representation. And so whatever task I do on top of these, I cannot adequately compute the functions that I may need to compute. Good. It's not ideal, and we were looking into ways of going beyond 1WL, right? So we already know that there are some message passing neural networks that can match the power of 1WL, but this is all, right? To go beyond, now we have to do something different. Can we grow this class? Well, there's one very, say, simple trick to go beyond the expressive power of 1WL, and that's the trick that I will start explaining now. For now, we assumed when we looked at this counterexample that was consisting of two triangles and one hexagon, we assumed that the initial colors were the same, right? They were all blue, let's say, yeah? And in this case, it wasn't possible to distinguish them because when you make an update, you rely on the node's own color, right? And on the neighboring colors, which were all blue. So you had two blue neighbors and it itself is blue, so the same update, basically. The question is, what happens if I had started with some different features? So color I'm using as an abstraction to represent features in this case, right? We already see the analogy between the WL test coloring and the features, right? This is the analogy here. And now imagine that I have some features that are already a little bit different from one another, right? Not uniform. And you can already see, like, if I apply the first iteration of the 1W algorithm, not message passing neural network at this point, I can already distinguish the graphs through the yellow nodes, right? So you look at one of the yellow nodes on the triangle. The neighbors I have is like one red and one blue, right? Whereas on the hexagon, one of the yellow nodes has only two red neighbors. The other one has two blue neighbors. In both cases, these are different than the neighbors of the yellow node on the triangles, right? So if I make an injective update, then these graphs will already be distinguished. Is this clear? Right, good. Now, if I do this for one more iteration, you can try this, then all nodes will be distinguished. And if I just draw the histogram of these, color histogram of these graphs, they will be different, right? And so 1WL actually can distinguish these graphs if I start with different colorings. Now the question is, can we do something similar for message passing neural networks to achieve this kind of power? Well, I can maybe set the node features, right? So I have a little bit of degree of freedom in setting node features. Usually they come from the domain, so this is important to notice. So we treat it as an input normally, right? So it may represent some special domain knowledge about this node, and we take them as they are. But it doesn't have to be that way, right? So I can make it as a model component, and I can modify the features before I run my message passing neural network on it. And one idea I can do is I can just plug in identifiers, right? So I can, it's like giving names. It's like giving IDs to each node. And this has been done in the literature, so I can just make sure that I give unique names like ID1, ID2, ID3 to nodes. It's a bit like giving an order to the nodes. Sorry. And then the models actually are very expressive, right? So there are many results about this that show that once we identify the nodes, we actually have a very high expressive power, things like Turing completeness and so on. Now, what is the problem with this? So why don't we use this as a model then? Wouldn't it be better to use this as a model? Well, we hard code these features now, right? So we give some IDs, and imagine you see a different graph at test time. We have to come up with IDs now. But IDs, we made them up, right? There's no meaning to that. So we just came up for them for the sake of distinguishing graphs. And there's no principled way of attaching IDs to nodes because there is no order over the graph nodes. This is where we started from anyway, right? And so if you try to generalize over such a model, it will fail miserably because there is no property that you can generalize over, right? You're just putting some IDs. And it's also hard to generalize over these kinds of deterministic hard-coded features. Now, one kind of relaxation we can do, and this is something we did in one of our works, is that we can inject some randomness to the initial features. So maybe there are some initial features. We can inject either a little bit more, a little bit randomness into some existing features, or append some random features to the vector. Doesn't matter. So the whole idea is we want to have some randomness in the features, initial features. What is the idea? The idea is, let's say we draw these random features from some Gaussian noise. The idea is that we will still use the actual features, but there will also be features that will allow me to differentiate from the other features. Because with very high probability, now the features on the nodes will differ, right? Because I'm drawing them from this random distribution. Good. Then the question is, what would be the expressive power of such a model, right? The intuition suggests that maybe I get the same kind of expressive power that I get from giving IDs without the need of giving deterministic IDs. But to formalizing this, we have to be, again, a little bit careful. The question is, well, now we are dealing with message passing neural networks with some sort of random node initialization. Yeah, this is the architecture now. And we are interested in understanding the expressive power of these models. And we are interested in posing the question in a more classical function approximation sense, yeah? Not in the sense of graph distinguishability, but in this case, they are pretty close. But because the message passing neural network now computes a random function, we have to define certain things. First of all, we have to say that, well, this computes a random function, so the output of this is actually now random variable, yeah? And so we have to talk about randomized functions and approximating randomized functions. Let's say we are given a randomized function f that associates with every graph g of order n, a random variable, f of g, is an epsilon delta approximation of the original function f. Sorry, which one was the original function? Yeah, so no. Yeah, original function f, if for all graphs g of order n, the statement holds. And what does the statement tell? The statement tells me, so I have two functions. One is the randomized function, the large f, right? The other one is the function that I'm trying to approximate. I want the output of these values, these functions, when applied to the same graph, to be epsilon close to each other, right? And I want this to be true with very high probability. That's what 1 minus delta shows me. This is classical epsilon delta function approximation for random functions. And in this case, yeah, because this large f is computed by a message passing neural network with random node initialization, we can say that this message passing neural network epsilon delta approximates the target function f. So we can actually speak of function approximation using this notion. Good. And what is the statement then? Given this preliminaries, the result basically shows that yes, this is actually possible. So take for any n greater or equal 1, and we are interested in invariant functions on graphs of order n. So this is important. We don't allow any graph, but we limit the graphs up to size n. So there has to be some upper bound. So we are operating on the bounded graph domain. Then for all positive delta, we choose there exists a message passing neural network with random node initialization that epsilon delta approximates this target function f. Yeah. So for each function, regardless of what the function is, we can actually come up with a parameterization of our network now that epsilon delta approximates the target function, right? So you can see this as a slight generalization of standard function approximation of MLPs. because we are looking at the probabilistic approximation now, right? So it's not deterministic. Okay, the key takeaway, as long as we are in the bounded graph domain, as long as we don't allow any arbitrary size graphs, this can be approximated. So what is the drawback? The drawback is the construction can be very large. Much like the universal approximation theorem of MLPs, the construction here can also grow exponentially. And yeah, it's not a friendly construction in any way. Now, but there is a more subtle discussion about this because we injected randomness to it, right? Is the model still permutation invariant? Because the proof the result relies on the fact that we individualize the graphs. What does that mean? With high probability, every node will have a different feature, right? Distinct feature. This is what I'm relying on, right? This was what we were trying to do. Kind of getting different enough colors so that the graphs become distinguishable in probability. This is what we wanted to do. But by doing this, did we hurt invariance? Because now, what happens to isomorphic graphs, right? So there's no guarantee now that I will map them to the same output anymore. So this permutation invariance that I cared a lot about initially is hurt, right? So it's not permutation invariant, strictly speaking. But the interesting thing here is because the model computes a random variable, the random variable itself is still invariant. Yeah. So the outcome of the computation still does not depend on the specific representation of the input graph. So this is a good property. So this is why we have the model still kind of permutation invariant in probability. Yeah, it doesn't hold deterministically anymore, but in probability it holds. Yeah. In this sense, it represents some kind of trade-off that well, if you want to operate on bounded graph domain, then it gives you universal function approximation and preserve some of the inductive bias that you care about, namely permutation invariance, but only in expectation and not deterministic. Good, so this was, like a simple kind of trick that you can just do. It's not very costly. There are certain drawbacks. The convergence, when you train, it gets slower. The construction, as I said, is very large. It only works on bounded graph domain, so there are many limitations of the result. But the good thing is that it's more scalable and tractable. But there are other extensions. There are many extensions of graph neural networks that are tailored for more expressiveness. And one of them is higher order graph neural networks. And we will see that these networks are not as scalable. And this goes back to the question that was asked at the end of the previous lecture. So a little bit of preliminaries before we dive into these architectures. We care about graph invariance and node invariance, right? Implicitly, what we care about is, let's say we have a graph, G, and for all isomorphic graphs, G and G prime, if we have a function, say xi, and we apply this on G and G prime, we want the output to be the same. This was the permutation invariance that we discussed on graph level. Now, equivariance is on node level, right? So we can define this as a node invariant as well. So in a certain formal sense, all that we care about is to compute a node invariant. And this is defined as shown here. So it's a function xi defined on graph node pairs such that for all graphs G and G prime and all isomorphisms F from G to G prime and all nodes in G, it holds that when we apply xi on a node U on graph G, it has to produce the same output after applying the bijection on graph G prime, right? So this is just essentially the same definition that we've been looking into. It's just cast as a node invariant. Essentially, the one that both what the WL test and the message passing neural network computes is a node invariant because we are computing node features, right? What they are computing are node invariants, so they are actually satisfying this condition. No, we know that. But are we limited to computing node invariants? Can't we just compute higher order invariants? And this is the fundamental idea behind higher order graph neural networks. So instead of looking at, so graph invariant can be seen as a zero array invariant, right? Because there is no node. Node invariant can be seen as a unary invariant, right? Because we are concerned about a single node. But we can generalize to this to k-array invariants. No? So we took, instead of looking at nodes, we can look at k tuples of nodes. Yeah? And we can define invariance over k tuples of nodes. Yeah? And this is basically what this slide here summarizes. And the nice thing here is that whenever we have a k-array invariant, we can always go down. So we can always do some kind of pooling or hashing, if you wish, to reduce it to k minus 1 array or unary. You know, you can always go down, but you can't easily go up without losing some information. Okay, so this is the core idea behind higher order graph neural networks. We don't want to compute just unary invariants, but we want to compute k-array invariants. And we care about the soundness and completeness as before. So whenever the invariant tells me that these two k tuples of elements are different, then there should not be an isomorphism from the respective graph to the target graph, right? This is soundness. Whenever it says no, they are not the same, the answer must be correct. Yeah. And whenever they say completeness is the same criteria, whenever it says well, they are the same, then there must exist an isomorphism from one to the other. If both of them are satisfied, then we say, you know, sound and complete. The invariant, because it's an invariant k-array invariant by definition, it's always sound, but it can be incomplete, much like the 1WL test, right? This can also be incomplete. Just because we are doing k-array, computing k-array invariance doesn't mean that it's going to be complete. Now, how can we generalize the WL test to compute k-array invariance? Well, instead of looking at it like I have a node and I'm looking at its neighbors, recoloring based on this and refining my colors as I go, I can look at the k tuples of nodes, right? So I can have a color for a k tuple of nodes. It's a bit complicated, I know, but and then I can define a new notion of neighborhood and look at the neighbors of this k tuple, whatever that means, and iterate over this algorithm. This would be the natural generalization. But how do we do that specifically? Let's say we start with k tuples of nodes. Yeah, so this is v to the k because we take a k tuple. And the KWL algorithm, there are many variations of this algorithm, takes a k tuple and gives it an initial color. So it gives it gives a final color at the end. And color is, let's say, represented as a 0, 1 vector, a d-dimensional 0, 1 valued vector. And it colors each k tuple of the graph using a d-dimensional color. So we start with some sort of atomic types. I will not go into the details of this, but it essentially encodes the initial type information of the graph. And then when we want to do updates, we need to this notion of neighborhoods. But now that we are not talking about single nodes anymore, but like k tuples of nodes, what's the notion of neighborhood? So if I'm looking at a k tuple, which is given by this v here, I know that it consists of v1 to vk, k nodes. I corrupt with respect to one position, let's say in this case the ith position, that's shown on the end of this slide. And this is considered to be a neighbor. So with respect to each position, I can corrupt with respect to each node, and this k tuple will be now considered a neighbor, right? So when updating the color of my k tuple, I look at all k tuples of this form, and you can imagine there are many, many of them, right? So for each position, I have v choices in the graph, and I have k argument positions. Yeah, so v to the k combinations. Good. And higher order message passing neural networks is one architecture that realizes this KWL algorithm. Not specifically this, it implements a different version of the KWL algorithm that's closer to the algorithm that's known as the oblivious KWL. But it's essentially the same idea. So what it does is, instead of looking at this as one WL GNNs or one GNNs, if you wish, so this is the classical one, it actually designs 3 GNNs. Yeah, this corresponds to a version of 2WL algorithm. but it can go up to 3 tuples, basically, yeah? And they basically present these results, alignment results with the WL algorithm and all that. It's an interesting, nice paper. But they observe when it comes to the experiments that the experiments are not really great because these data sets don't necessarily require that much expressive power, maybe, and maybe other reasons. And they also design a hierarchical version of this because when you reason about these k tuples and everything, yes, you get more distinguishing power, but you also may lose this kind of local node inductive bias because there is important information on node level, so you still may benefit from doing this node level aggregations. And so what they design is this hierarchical version of a graph neural network where they first apply the 1GNN algorithm and then the 2GNN algorithm and then the 3GNN algorithm, and this is kind of nested and pooled together to yield a unified algorithm. Right. Again, in practice, it's questionable whether this expressiveness is needed. There are contexts where this is really, really helpful, but it's not always helpful in every real-world graph. And on maybe one further comment about this. This holds also for the WL hierarchy and also for these KGNNs. The WL hierarchy is an infinite hierarchy. So as you increase K, you get more and more expressive power, right? There is always an example where you can create, regardless of how large you pick the K, if you pick K plus 1, you get more expressive power because you can construct a pair of graphs that cannot be distinguished by KWL, but it can be distinguished by K plus 1 WL. Yeah, it's an infinite hierarchy. And so the same holds for these KGNNs. So if you design a KGNN, it doesn't mean that you have all expressive power. You will still be less expressive than the K plus 1 GNN, if you wish. Good, yeah. The main problem with these architectures is that they require excessive memory and computation time to run. So this is highly intractable. As I said, they roughly require V to the K memory, and this is, yeah, very damaging, you can imagine, especially in large graphs. And even if K is 3, this already is very, very bad. And that's why they only implemented up to three GNNs, and they used a lot of approximations and memory improving tricks. Good, yeah, KGNNs are expressive, still limited. The inductive bias, well, they are permutation invariant. Of course, they don't lose any of these properties. But the hierarchical version of the algorithm seems to be working better because it keeps both the node inductive bias that you get directly aggregating for the node and also the expressive power from the higher order message passing architecture. That being said, this is not the only option. So if you want to implement some sort of carry invariance or some sort of higher order kind of refinements, you don't necessarily need to rely on message passing algorithms. So this is an interesting work because what we can do is we can just rely on k-order tensors instead. Remember how we design, say, simple neural networks. So we look at linear layers, right? And we put non-linearities in between. And the same can be done here. So we can take a bunch of linear layers with non-linearities in between. But now these linear layers will be represented with tensors. Why tensors? Because we would like to represent carry relations, right? So k tuples of interactions. So the interactions are not binary anymore. I need k tuples of interactions, so I need to use higher order tensors. More formally, we can define linear invariant layers as shown here. So what I'm interested in is defining an invariant layer. So what does that mean? It means when I permute the feature matrix, the result should not change. Well, yeah, I can parameterize such an invariant layer. And I can also define linear equivariant layers, similarly to before, using very, very high tensors, of course. And then the resulting invariant k-order graph neural network given by Maron et al. Has the following shape. So I have these equivariant layers, so d-equivariant layers that are composed. And at the end, I put an invariant layer, again, the classical trick. And at the end, I put an MLP for the downstream task, or as a decoder, basically. And that's my function. And the effect of this is essentially the same. In Maron et al., I mean, there's a lot of theoretical results in this series of papers, but he characterizes all invariant linear functions, and even gives the vector space that these functions live in. And this dimension is actually independent from the size of the graphs. It's related to the ith Bell number. And that's quite nice. It's more of a theoretical work, I would say, and it's invariant by construction, and it satisfies all the criteria we want. And it can already be universal with very high tensor order. So this is merely of theoretical interest. Of course, it has no practical value because this tensor order will be crazy, crazy high. There are alternative proofs of this universality result. But yeah, so this is just to say that, you know, if you want to achieve this, match this KWL expressive power, you can also do this without relying on a message passing algorithm, but instead relying on k-order tensors. The advantages and disadvantages depend on the context. Good. The limitations are kind of similar. Scalability and excessive memory requirement are the limitations of this approach. Good. Let's see how much time is left. Yeah, I still have a little bit of time. So maybe I can talk about these algorithms that are more widely used in practice, given by subgraph and homomorphism counts in graph neural networks. So let's go back to the picture that we have seen earlier, right? So we wanted to distinguish these two triangles from the hexagon, and the graph neural network couldn't do this. What does this mean? It also means that it cannot detect triangles, right? Because if the graph neural network was able to detect triangles, it would have seen that graph H has two triangles, whereas graph G doesn't have any, right? So it would have immediately separated them from each other. So this means that it actually cannot detect triangles. More generally, graph neural networks can actually not detect cycles. So this is a severe limitation, especially when it comes to making predictions with molecules and similar structures. And this is actually quite important for many real-world tasks. So the question here is, can we break 1WL expressive barrier by explicitly injecting useful information, not just, you know, random information, but like saying, for example, in this case, a triangle would have been useful. Just injecting on the node features or node level information that whether this graph has triangles or how many triangles this graph has. It would be useful, right? Because then I already have this information in the node features, so they are already, the graph neural network is informed about this, and it can discriminate these two graphs. Good, and that's essentially the idea with substructure counts. There are many different ways of doing substructure counting. One is based on extracting graphlets. Maybe I shouldn't go too much into the details of how this is done, but the fundamental idea is that we determine basically a bunch of small motifs or small subgraphs, like triangles, that we think might be important for the domain or for the application. The idea is that we will count these patterns and structures in the original graph and put the numbers into some sort of graphlet vector appended to the initial node features as an extra information, right? So we have the initial node features, we use them, this is fine, this is all good, but we also want to increase the expressive power of the graph neural network by telling the graph neural network through these new features that how many, say, triangles, how many 4 cycles, and so on, how many rings of a certain size this graph has. Okay, this is the fundamental idea. Let me skip this and just show you the graphlets. So a graphlet looks like this. So this is called the graphlet degree vector. So we look at a graph. In this case, the motifs we are interested in are given as A and B and C. So one is just showing, two nodes that are connected to each other. This is just a single path node. The other one is showing a triangle, and the other one is just showing us as a two-path motif, right? And what we want to do is we want to count the occurrences of these motifs that touch to a certain node in the graph, right? Like for each node, rather than just injecting naively the counts, we want to inject how many times this motif matches that node and inject specific information about that particular node. And in this case, the graph degree vector looks like shown here, but it contains a few technicalities, so I don't want to go through the technicalities. The main idea is just to encode the structure counts that are orbited in these nodes. And once I do that, I actually get a lot more expressive power. One seminal work in this direction is graph substructure networks that implements precisely this idea of injecting these subgraph counts as additional feature information to the graphs and increases the expressive power of graph neural networks. Good. But in the same line of work, instead of counting the induced subgraphs, there's a different way of counting. And this is given by Barcelo et al. A few years ago. And this is counting homomorphisms. Yeah? So we don't count the induced subgraphs, but instead we count the homomorphisms from one graph to another. It's just yet another option, right? And the curious question here would be, how do these compare? Because there are two ways of counting, and it makes sense to understand whether they have the same expressive power. One gives us more than the other, and so on. Turns out, I'm showing these examples here, but it's very hard to count because these numbers are very large, especially with homomorphisms. It's just very hard. We have examples that show that they are incomparable. So there are contexts where counting induced subgraphs gives you more, and there are contexts where counting the homomorphisms gives you more distinguishability power. So we have examples for both. And one recent work that we did actually showed that instead of counting homomorphisms naively, if we count certain basis motifs, the homomorphisms for basis motifs, we can actually become more expressive than both, right? So this was kind of an interesting finding, which is summarized here. So if you want to go beyond 1WL using substructure counting, we can rely on counting induced subgraphs, which is the work on graph substructure networks given by Bouritsas et al., or on homomorphism counting, which is given by Barcelo et al., both of which go beyond the expressive power of 1WL. So if we enrich standard message passing neural networks with these tricks, they both go beyond the expressive power of 1WL, but they are incomparable. There are certain things that one can do, but the other cannot, and vice versa. Whereas if we encode the motifs in the basis, then we get a super class, right? So we become more expressive than both homomorphism counting and induced subgraph counting. Good. Okay, so what are the takeaways from this more technical lecture? There are many different ways of designing more expressive architectures. These range from like very simple tricks like adding some unique identifiers, I don't know, some random features, all the way to KRE kind of message passing, computing explicitly KRE invariants, and to things like subgraph counts or substructure counts or homomorphism counts. And what works best in practice is quite debatable, and it probably also depends on the application, and is also domain specific. Generally the subgraph methods or homomorphism counting methods are much more scalable than the K-order tensor methods. They just don't scale usually, which makes them a little bit more viable in practice. But for most real-world tasks, the predominant choice is still like classical graph neural networks. So this is an important point to take into account. And with this, I would like to conclude the lectures for today on my end. I'm happy to take any questions that you may have. Yeah.
Why did we need to introduce invariant and equivariant layers rather than using the pooling? I mean, what advantage did we get by doing that?
I don't quite get the question. So you need
higher order message passing nets. We were first pooling. Say, I have 1 to k order neural nets.
So you need to somehow define a way of, you need to define the layers. So this is your computation layers, right? So you want to give a mechanism to update how, you have to tell how you're updating the representations, right? You can't just do this by pooling. Pooling is something that you do at the end, right? Like, so you already have computed the representations and then you can pool them, yes, but you have to first compute the representations. These are the layers of the network. And so if you want to realize a carry invariant, then you need to do this, say, either by carry message passing layers or using carry tensors in the invariant and equivalent layers.
Yes, so I'm saying that why are we using carry layers instead of carry invariants?
Well, carry invariance is just a notion. It's just a definition, right? It doesn't tell us how to do it. This is just a definition. What realizes it is the carry coloring, for example, or carry tensors or carry message passing. Yeah. That's what realizes the definition. That carry invariant is just a definition. Yeah.
Hello? Yeah. Thank you for the very nice lecture.
Thank you.
So my first question is, like, I'm curious how the expressive power of GNN scales with the dimension of node features. So, like, this might be my naive thought, but like what thought I had was, if you take node features and train a variational autoencoder and then take the neat like representation and do like use that for GNN message parsing, like would that yield better results or yeah, basically how does the expressive power scale with the dimension of node features?
So all of these results hold pretty much independently from the dimensionality of the node features. So the expressive limitations that I just discussed are independent of the dimension. So if you take larger node features, that doesn't change anything, unfortunately. So for example, this 2 triangle versus 1 hexagon example, as long as the features are the same, the dimensionality doesn't play a role. Does it answer your question, or did you mean something?
Yeah, so but like I get like theoretically it doesn't depend on dimension D, like all the results that you saw.
Yeah.
But like practically, like when you deploy these algorithms, so could you project your dimension of nodes to a higher dimension, and would that give like better results as opposed to using the node features in that specific dimension D, or not?
From an expressivity point of view, again, it doesn't make a difference when you project it to higher dimensions, because if 2 features are the same, when you project them to the larger space, they will still be the same, right? And all that you care is whether they are different or not. Like, you don't really care how they exactly look like, right? In that sense, it doesn't change anything. But this is just increasing the parameter counts. Maybe that has an effect on some practical, in some practical context, but not in this theoretical setting.
Just like last question, simple. Why do we care about counting homomorphisms?
Well, it's just a different way of counting substructures, right? It's an alternative way, and turns out that it's counting induced subgraphs gives you a different kind of expressiveness gain compared to counting homomorphisms. So they are incomparable, right? So it makes sense to look at both. But what I've shown at the end is, if you look at the basis of these motifs that you care about, then you kind of subsume both. You can get the expressiveness gain that you would gain from both. So that's kind of like probably the right way to go. Thank you.
So in the 1W case, where the starting colors are random, is there a guarantee that the graphs that are isomorphic will converge to like the same histogram? like will report this identity?
Right, so it's a very good question. So if I'm given two isomorphic graphs, let's say in this randomized message passing neural network setup, will they eventually converge to the same value? Well, in expectation, right, they will oscillate around the same value, but exactly same is not easy, right? So having them exactly same, not, but like you keep on resampling this randomization, and if you iterate over this thing, it indeed oscillates around the variance. So we have, I mean, there are results on this presented in the paper. So it actually, the variability helps you to distinguish the graphs, but the mean is around the same value always. So it shows that it's actually invariant in expectation, but the slight variability helps you to distinguish the graphs. So it's kind of a trade-off. And it turns out that if you randomize too much, it actually hurts. So if you do it a little bit, like if you do some partial randomization, even like single dimensional randomization, gives you enough variability, and yeah, that's enough. And then for the rest, you stick around the same mean. Thank you.
Thank you for the great lecture. And my question was, in the KWL algorithm, we have k nodes in the double, right?
Right.
And how are the nodes selected? Are they selected arbitrarily, or they are or are the nodes adjustable?
Also very good question. So I didn't go into details of the KWL algorithm because first of all there are many variations of it, and it's hard to grasp on the fly, and depends on which variation, like which algorithm we take. There are different strategies to pick these k nodes, but in the classical one you just take all k tuples. That's why it blows up with v to the k. So you have to take all k tuples of nodes. That's yeah, very huge space basically. Yeah, I guess those are all the questions. Yeah, thank you very much for listening.